So let's start with a motivational quote. Life is a single-player game. You're born alone. You're going to die alone. All of your interpretations are alone. All your memories are alone. You're gone in 3 generations and no one cares. Before you showed up, nobody cared. It's all single player. It was from Naval Ravikant. Are you motivated now? Am I doing this right? Yeah. So really this quote is more to motivate the talk than to motivate you, although I hope you are motivated to live your lives at the fullest now. So let's say this is a cluster, and when we think of a cluster, what we think about is like, nodes, and we think of them, and we have this view of the node being, the cluster being all these nodes. We have this sort of God view where we see everything. But the reality of it is we don't see everything. What we do, we run software, and the software runs on each single node. So what we see is other nodes, or maybe, something happens and we don't see them, and we don't know why we don't see them. Maybe the network is gone, maybe the process on the other machine is gone, maybe it's a JVM and it's garbage collecting, who knows? But that's the reality of it. So really what I want to discuss here are the how of building clustered system, distributed systems. So there are 3 key issues here. The first one is we need to know who is there, discovery. Who else is there with me in the cluster? Who else should I consider a part of the family? And then there's fault detection. What if someone crashes? How do I know about it? Can I rely on the other process to be alive or not? And then finally, load balancing, because that's one of the reasons why we do all of this distribution, is because we want more computation power than a single node could give us, where we have scaled up vertically at the most, or it doesn't pay off, so we go horizontally. That's one of the main motivations for going into distributed systems. And if we want to do that, then there is one abstraction that's quite powerful. That's the one of group membership. Okay, so that group membership abstracts over these 3 key points and lets us sort of, when we have this service, we can answer all of these questions. And if we want to implement group membership, we need 3 things. Again, we need failure detection, we need dissemination, a way to get the word out of information, spread information around the cluster, and then we need consensus. And this is what this talk is going to cover today. So let's start with the first one. Which album is this? Wish You Were Here, yes, great. Wish You Were Here, 75, great album. And that's failure detection. For some reason, failure detection is one of my favorite topics. In this sort of space, I have an irrational interest for failure detectors and failure detection mechanisms. But so let's get started with some definitions. And there's 2 main key properties, I should say. The one of completeness. So if a process fails, you want everyone else to know that this process has indeed failed. Completeness means that everyone knows, okay, this guy is in trouble. That's the first one. And the second one is accuracy, which is to say that we don't want healthy processes to start suspecting other healthy processes of having failed. So we don't want false positives. And then, that's the theory, and then when you go into practice, you have other things like, speed, latency, network message load. These are sort of necessary evils that we also have to factor in when we design failure detection protocols and mechanisms. So what happens is we want to build this. So when we want to build something in the distributed system space, the first thing we do is we sort of get an impossibility result which tells us that we can't do that. So it's impossible for a failure detector algorithm to deterministically achieve both completeness and accuracy over an asynchronous unreliable network. The types of networks we have are inherently asynchronous and unreliable. So basically we can't do this. We can't have a failure detector which is has both completeness and accuracy. So what we have to do is we have to make trade-offs. So we distinguish between strong to weak completeness, where either all or some non-faulty members detect a crash, and strong to weak accuracy, where there are either no or some false positives. And what happens is that in practice, applications prefer to know that, they go for strong completeness, and then they trade off on the accuracy. So they go for something like strong eventual accuracy, where there are going to be some false positives, but at least there is not going to be this question in the air whether a crash process has not made it to, the knowledge about a crash process has not made it to all the members of the group. There is a few strategies we can use. The first one here is we use a heartbeat. So we just send a signal out. Are you alive? Are you alive? Are you alive? And then if we don't receive, or that's actually not are you alive, it's more like I'm here, I'm here, I'm here. And if I don't get a heartbeat, it means the other process is gone. And the second one is sort of a ping pong request response style, so where we say, are you alive? Yes, I'm here. Are you alive? Yes, I'm here. So these are two strategies that we can use to, on a pair-to-pair basis, detect whether a process, another node is there or not. So now let's talk, after this, let's talk about a few failure detectors. One that has a very cool name is the so-called Phi adaptive accrual failure detector. It's used widely because it has a cool name. Cassandra sort of made this popular because they were looking for something that could scale. Facebook made this popular because with Cassandra they needed something that needed to scale over hundreds of nodes, and they couldn't find something. So they found this, and it sort of scales, sort of. And it's adaptive. It means that it adapts to changing network conditions. So if the network sort of is in trouble, it also tries to, it takes that into account. It doesn't assume that the network is always going to have the same properties over time. And it introduces the notion of accrual failure detection. And accrual failure detection means that you don't just have two values. You don't just have this distinction of, hey, this is failed or this is gone. I can trust this or I can't trust it. It's not this binary thing. It's a value. It's this phi value, which sort of says, well, I think maybe, sort of it's a probability that the other node is there or not. And then the application can decide what to do. So, for example, say that we have a master and then a few worker processes. So we would say that if the suspicion level gets a value greater than 8, we stop sending new work. So that's assuming that the master gets this, has this failure detector, and it gets these suspicion values of the workers. And then the worker, when the threshold, the value is greater than 8, we would stop sending new work to that one worker. If it's greater than 10, then we sort of already lose hope, kind of, and we start rebalancing new work and sending it off to someone else. And then when it's greater than 12, we just give up and remove the node from the ring. What you may notice on the slides here on this, I don't know if you can see this very well, but the higher the threshold, the higher the detection time. Or the lower the threshold, the faster the detection time. And again, that's a trade-off, because the higher the threshold we use, the lower the failure rate, but the lower the threshold, the higher the failure rate. So basically, you have to make a trade-off between these two things. There's a kind of a sweet spot between 10 and 12. If you're using AWS or cloud in general, you go to 12-ish, something on that side, and then if you have your own real sort of network with real stuff, you go for 8 or 6 or lower. You have to experiment and tune that. The Phi adaptive accrual failure detector is used in Akka, so you can sort of change the value according to what you run this on. And you shouldn't just use the default, you should adapt it to what you're using. There is another one called the new adaptive accrual failure detector, not such a cool name. It's also an adaptive accrual failure detector. The only difference to Phi is that it's much simpler to implement. It's much cheaper to calculate the probability, the suspicion value. So I played with this a bit. I implemented it for Akka, and it's slightly more adaptive. So in the cloud, it performs slightly better, but overall it's the same principle, the same idea. We don't change much there. Now, one really nice one is swim. So the swim failure detector says that as you swim lazily through the milieu, the secrets of the world will infect you. And this is one of these computer science papers which cites a biology paper because it uses infections and spreading of infections in populations to sort of doing things. So SWIM has both a dissemination and failure detection component. Now I'm going to only talk about the failure detector part. Dissemination will go in the second part of the talk. And what they wanted to design is a scalable membership protocol, something that, where you don't pay the price of having hundreds or thousands of nodes with speed or accuracy. And the way in which SWIM does this is, well, first of all, it's going to not right away remove nodes that are suspected. It's just going to first suspect them, and then there's going to be a chance for the node to still be part of the family, which increases stability. So how does it do it? Well, let's say this is a very quick description of the SWIM protocol. There's a ping message sent at random from one node to another. And then let's say that the acknowledgement is lost, or the node was running Java with a garbage collection or something. So the ping goes there, the acknowledgement is too slow. So this node that sent the initial ping, what it will do, it will start this ping request. That's another type of message. And it will send them to 3 random nodes out there. And those in turn will try and ping the original node, which might then be able to reply to one of these intermediary nodes, which can then reply to the initial one. And then the result is that we don't suspect that node of having failed. We found a way around it. We found a way to not suspect the node. Now that paper and that mechanism is quite elegant. Now the only thing is, in real life, it's not that efficient. So what the people at HashiCorp did, they do things like Terraform, Console, Vault, I don't know if you've heard of that, and they devised something called Lifeguard on top of SWIM, inspired by SWIM, on top of SWIM, because with SWIM you still get a lot of false positives, okay? So the implementation is open source, called MemberList, written in Go, and they added 3 optimizations to SWIM. And so what you can see here is that this is the baseline L0, and we still have quite a few events here. And then if we add all the optimizations, at the end of the day, we have less than 2% of the false positives of vanilla SWIM. So that's pretty great. I haven't found anything that is better in terms of scalability, latency, false positives so far. I mean, maybe there is, but I haven't found one yet. So that's a pretty cool protocol, I should say. And that is all about failure detectors. I could go on for like days, but I will stop here. And now that brings us to our second part. What album is this? Pulse. Pulse, dissemination, you will see in a second why we say that it's pulse. So what is dissemination? Well, we need to be able to answer these questions. We need to communicate about members joining, members leaving, and members failing. We need to be able to spread out this information. Now, there is a few strategies, again, that we have at our disposal for this. And the first one is multicast. Now, if you look for multicast, what you find is things like this. Just saw the phrase multicast support and a chill went down my spine. Or here, this one, which is straight to the point, sort of. The almost uniform inability to support multicast on today's networks is such a humiliating defeat for distributed systems. I just had this conversation today. So it turns out that there is multicast in theory, but not quite so much in practice. So what happens is there is different levels at which we could have multicast, hardware, IP, UDP, and if you, in practice, go to the people that run the data centers and you, hey, we need multicast, and they go and no, you don't get multicast. And even if you had multicast, it turns out that if you need things like total orders, a total order of operations, if you care about order, in a multicast, with multicast, that's notoriously hard. There's a 50-page report by Xavier Defagot and it's quoted down there. If you're into this, it's quite hard to sort of get some of the guarantees out there. So what do we do? Who remembers this company? Yes. So Napster. In the good old days, we downloaded legally, completely legally, MP3 files using this, and this is pair-to-pair. Okay, so we form a huge ring, and then we sort of transmit information. Now, with pair-to-pair, you can only talk to directly from one node to the other. So search, there is quite a bit of research that has been done in these days, Chord, other algorithms of the kind. So how do you search? How do you broadcast across a pair-to-pair network? How do you optimize it? You have overlay networks, you have all sorts of things you can do. Turns out there's a few gossip styles that we can use from there. The first one is random gossip, where we just pick one other node, one at random, and at each tick of the clock, 0, tick 1, tick 2, each node gossips to another node at random. And that turns out to spread quite fast. But we can do better. So there is round-robin gossip, where round-robin is not necessarily better, simple round-robin. It's more deterministic, okay? We know exactly which other node should get the gossip next. In binary round-robin, we do the same, but it's faster. And then we also have round robin with sequence check, where we can, we use the deterministic nature, and then we can even predict the failure of a node just by it not gossiping at a certain round. You could build a protocol on top of that. For some reason, nobody picked that up. It's not being used. I don't know why, but it's there. It could be used. And then there is Swim again, which does something quite different. It's using this infection-style gossip. So it sort of infects, it piggybacks on top of the existing protocol messages, the ping, ACK, ping request, etc. And on top of these messages, because these messages are really small, there's still in the frame, there's still some space left. So you can just add some information there, and that's how you gossip. That's how you add information and spread information about the cluster. So it's more, you don't have a dedicated gossip in Swim. There is a dedicated gossip message in Lifeguard, which they have added, but not in Swim. All right, so but then the question is, what do we even gossip about? Let's say, that's a simple form. We have node A, which has a table, and the table represents when a node has been seen for the last time. So A is A, so it saw itself 0 seconds ago. It saw B 1 second ago, and it's seen C 3 seconds ago. And then let's say A and B, B, on the other hand, has seen A 3 seconds ago. B, it's B, so it has seen it 0 seconds ago, and then C B has seen C 1 second ago. Now, if both of them were to exchange these tables, what we would end up with is A and B have seen each other at 0 seconds ago and C at 1 second ago. What you can do when you sort of transmit that is you can say, okay, the moment someone crosses a threshold of 5 seconds or 7 or whatever, I'm flagging that as a failed node. And everybody has received this table, so everybody implicitly knows that they have, that this node is gone. That's one of the, it's a gossip-based failure detection protocol. It's one of the seminal papers on this sort of approach, I think. So next to that, there's quite a few things you can do in order to optimize gossip. So here's a few concrete examples of what you can do. For example, in Akka Cluster, Akka Cluster maintains a list of nodes that have seen a certain version of a gossip. So it can gossip with a higher probability to nodes that have already received, that have not yet seen the message. So that way it doesn't just spread things randomly, but it's biased. Also Akka Cluster, when less than half of the members have seen the latest gossip, it speeds up the gossiping. And that would be the case either when the cluster is being bootstrapped or after a network partition, when the cluster is sort of recovering and noticing, hey, I need to go faster, I need to spread out, I need to consolidate my state. In Lifeguard, they have an anti-entropy mechanism that where one node will pick at random another node and do a full sync via TCP/IP, because this UDP-based gossip it's just entropy. So anti-entropy means we just make it less random. And that sort of also speeds up convergence after network partition. Okay, what's this album here? That's a hard one, because I think it's not under the cover, it's sort of in the back of the... Yes, a momentary lapse of reason. 87. I've used that for this topic, which I hold dearly. So this might be a bit dark, but still. So he who fights with monsters should look to it that he himself does not become a monster. And if you gaze long into the abyss also gazes into you. Nietzsche I really like Nietzsche. So if you don't know Nietzsche yet, there is a book called Hiking with Nietzsche that just came out, which is pretty great. It's not about distributed systems, but you can apply some of it sometimes. And you know, that's sort of, we realized about after a few years that no matter what we do, at the end of the day, we should just all go out and hike and do things like this, and not just spend our days in front of the machines. But you know, this is from a practitioner's perspective. It's sort of, consensus is subtle, so it's not so easy. We're still not done yet. There's still, I think we can do better. So one of the first things is here, again, if we look into consensus in the context of building clusters, again, we have an impossibility result derived from FLP, which is to say that group membership with a single group, so with a primary partition, is impossible when there are nodes that are suspected of having failed. The moment that you have one failed node, you don't have a group membership anymore. You don't have consensus on the group. So what does that mean, and what does that mean for us? Well, what it means that if it wouldn't be very wise to continue doing membership-related decisions while the cluster is in this unstable state of having failed nodes, because if we do that, then we end up in a world where not everybody sees everyone else as being part of the group. So then we don't have one cluster anymore. We have this sort of split, whatever, schizophrenic cluster, which we don't want to have. So the question then is, how do we reach consensus? How do we manage to do that? Well, the first thing we want to talk about is time, because we have to start thinking about reaching consensus on time. So I would say the most important paper, if you're not at all into reading papers, the most important thing to read here is I think, this paper here, Lampert clocks, and this is about how do you order events in a distributed systems? How do you establish an order between things happening? And this is a very rich paper. It's sort of really introduces quite a few concepts. I think this is really important. So if you only want to take one thing home from this talk, is this paper here. Leslie Lampert's Time, Clocks, and Ordering of Events in a Distributed Systems. In my opinion, this is a must read. Then Lampert clocks, they're good, but they don't sort, they can't establish a total order. They can't establish a way of saying, and they can't sort of detect whether two things happened at the same time concurrently. So for this, you need vector clocks. And this is a way, so basically it's a vector of Lampert clocks, and that way you can detect that two things have happened concurrently. And then there is version vectors and dotted version vectors, which are an evolution over version vectors. And they're quite similar to vector clocks, but the semantics, they differ. So in version vectors, you are interested in detecting conflicts, whereas with vector clocks, you want to detect things that happen concurrently. So it's about events versus different versions of data. There is a post on that. Version vectors are not vector clocks. They look quite similarly. They've been developed by two different groups of researchers in parallel, sort of, and there are two different things. and they differ quite a bit in the implementation. Vector clocks need to maintain the state for all eternity versus version vectors could just get rid of some of it. And just to show you some code, there's one slide with code here. No, there's going to be another one, I think. Anyway, so just to show you some code and to show you that all I'm talking about is not something just theoretical. This is Akka Cluster's gossip. And what you see here, this version here, or over there, this version here. This is a vector clock, okay? So Akka Cluster uses a vector clock internally to figure out what the version of a gossip message is, so that when two messages, sort of when two nodes exchange a gossip, we can say, hey, this happened before, is an older version, so I'm updating my state, or this happened after, so I'm ignoring this and I'm sending back the newer version of the gossip to the node that sent me this, or it's the same, and if it's the same, we need to merge. We need to sort of go in there and see what happened and merge the membership ring and figure out how to do that right. Now, another very important concept is the one of replicated state machines. So about state machines, what we can say is that any sufficiently complicated model class contains an ad hoc, informally specified, bug-ridden, slow implementation of half a state machine. I really like this quote by Pete Ford. Who likes state machines here? Likes working with them? Yeah, that's great. It's state machines are great, really, really great tools. I don't know many places that should use state machines don't. I'm not sure why. But so if we talk about replicated state machines, the idea here, and that's again something that Lamport sort of reported first in his paper, like the time clocks and the ordering of events, it sort of introduces the concept of state machine, the replicated state machine. So what is this all about? Well, we have a client here that talks to servers, and what we want to achieve is a fault tolerant copy of that value. So what we can do, we can send up values in a certain order, and they're going to be replicated to all the servers in a certain order, and they're going to be applied up there to these state machines. And since we know the order, we can use vector clocks and such to guarantee the order. We can apply them in order, and when we apply them in order, what happens is we get the same state at all three places. So in principle, that is quite simple, right? That sounds quite simple, but in practice, we need a protocol or set of protocols to make that happen. So this is where consensus protocols come in. So the idea is to have fault-tolerant distributed systems, replicated state machines that allow to store values. I have a mouse pointer now. That's interesting. And the point here is to agree on one single value, okay, amongst many machines. And so there is quite a few set of such protocols: Paxos, Raft, Flexible Paxos, CAS Paxos. There's also Fast Paxos, I learned, and there's many more things. It's very interesting. Most of them are based on a log. So here you see sort of I think this is Raft. This is a log. So you see there is the concept of a leader, and in most cases, and a log of values, and then at some point you sort of commit things to a log, and you get a. I'm not going to go into explaining this. I can't explain this in the scope of this talk, but this is how you agree on values. All right. Now, if we look into other types of ways to reaching consensus, there is one mechanism called conflict-free replicated data types, which is very interesting as well. And that guarantees strong eventual consistency, which is to say that eventually you will have the same value everywhere, even if there was network partitions or crashes, you will end up with the same value. And the way this happens is, for example, let's say I have 3 nodes, x1, x2, x3. They all start with the value 0. Okay. And then on node 1, on node 1, yes, I set the value 1. On node 2, I set the value 4. And on node 3, I don't do anything. Now I'm going to propagate these values about, so for example, I'm going to send 4 to node 3, from node 2 to 3. And what I'm going to use is I'm going to use a merge function, which in this case is the maximum. So the maximum between 1 and 4 is 4. So the value is 4. I repeat here, I send 1 from node 0 to node 3. So the maximum between 1 and 4 is 4. Sorry, before this was 0 and 4. So now the point here is that I have 4 in the third node. That's my result. I can send the value 4 also to my first node, and then I do the max, and the max between 1 and 4 again is 4. At the end of the day, all of them have the same value. So the state has converged by virtue of the fact that max is a monotonic function, which is to say it is only growing in one direction, either up or down. So this was a convergent CVRDT. It uses convergence of state. There is also CMRDTs, which use commutativity of operations. For this to work, you need reliable broadcast, which is not that obvious. And so CVRDTs are quite popular. You have a CVRDT implementation in Akka Cluster called distributed data. And then my preferred way of reaching consensus is just by not saying anything at all, by not sending information out. For example, a quite elegant way here with Akka Cluster is the leader designation. So the way that's done is just by saying, okay, let's take all the nodes in the membership ring. We have agreed on these. They have been, we have converged. These have been sent around. And so the leader is gonna be the node that has the, we sort them by address, by IP address simply, by network address. So that's sort of a deterministic order. We remove the nodes that are not in the right state, like down or so we put them at the end. And so at the end of the day, everybody will find the same leader just by looking at their gossip information. There is no need for a leader election in this case, it's just some designation. So that's quite powerful as well. Sometimes you don't need to talk to make a decision by just using some properties. All right. So let's talk a little bit about a practical part here. I want to talk about Akka Cluster. So Akka Cluster, if you look at the architecture of Akka Cluster, at the bottom here you've got this membership mechanism, let's say. That's the core of Akka Cluster. It gives you the membership. That's what it gives you. It tells you who is there, who is not there, who is in trouble. On top of this, you have all sorts of components. Distributed data, these are CRDTs. Cluster singleton, that's one feature that guarantees that you only have one process or actor running in the whole cluster. It guarantees that. There is a mechanism in there to do that and to hand over. It also sort of passes, if that node crashes, the singleton gets recreated someplace else. So that's a good thing for failure recovery. Sharding lets you, if your actors, if your process have many things in memory, it just lets you shard this data out on multiple nodes in memory, and it takes care of splitting them across, and if one node fails, to sort of rebalance the failed shards and recreate them on the other nodes, or if you add more nodes to sort of balance this out. So this is all taken care of by Akka Cluster in this regard. And then on top of this, you want to build your application. There's also another class of component that I forgot to mention here, distributed routers, cluster-aware routers, so you can distribute workload around across your cluster. So that's pretty cool. So how is it built? How does it work? Well, the failure detector is the phi adaptive accrual failure detector with a ping pong strategy, with biased, the dissemination is random biased gossip. You can set the bias, you can also set the bias threshold, you can change the bias When there is more than 400 nodes, I think, you can sort of change how that works, because the nature of the whole cluster changes when you grow it in size. Now, in terms of consensus, the leader is reached by convention. There is no election process. And all the membership decisions are driven by the leader. So the leader says, okay, now this node is part of the pack or not. This is all the leader has the last hand on that. There is also another failure detector that you can configure, deadline-based one, simpler one. Sometimes it makes sense to use it. But phi is by default active. Now, how does life for a cluster node in Akka look like? Well, we have this state diagram. Let's look into this a bit more. So the happy path is I want to join the cluster, so I'm joining, then I'm up. Then at some point I decide to leave, then I'm leaving, and then the leader says, yes, you're ready to leave, then I'm exiting, and then again, the leader says something and I'm removed. That's if everything goes according to plan. Now, in reality, that is not what is happening. Sometimes you get the sad path, where you join, the leader says you're up, and then something happens, the failure detector sort of detects that something has gone wrong, and you're in this pseudo state unreachable. It's not really a state, it's just, you're not there. And then you go down and you're removed. Okay, so that's what happens in case of failure. And the big question here is, how do we get from unreachable to down? Okay, who makes that decision? So you can either do that by hand, by just having someone monitor the cluster 24/7, that's one option. Or you can use a split brain resolver algorithm, that is also another option. And I could probably talk about split brain resolvers for 1 or 2 hours, but I don't have time, so I'm gonna skip that now. So where do we go from here? Taking all of this into account, and I wanna sort of finish this talk with moving out a bit of what we do. Well, when we think about it, because I mentioned Cassandra, I mentioned Akka Cluster, I mentioned Console, there's quite a few technologies that we use. At the end of the day, we all deploy these cluster nodes on physical machines, on physical servers, okay? So we have these servers, and we probably want to collocate an Akka application node with a persistent Cassandra node. Maybe we use something like Kafka, which uses Zookeeper. Maybe we deploy this and coordinate services on a machine using Console. So we'll have this one physical machine which has all these nodes. I could have mentioned Kubernetes here. You could also just have the server and then Kubernetes and then all of these things on top of Kubernetes. And Kubernetes would also have use etcd to coordinate things. So the point is we have several physical machines and they all have these nodes, and then what they all do is they all talk. They all want to know, is there anyone there? Who is there? Are you still here? I'm here, can you hear me? Hello. They all do the same thing, okay? Everybody does the same thing. And it's the same question. So it's different services, but it's the same question that we want to answer. Yes, there are differences in maybe gossip frequency and the nature of what is gossiped about, but all of these things, it's kind of can be abstracted. And so if you look into this, I want to sort of point the attention to what happens to our world as we build systems. And this is sort of what happened in the past 100-something years in terms of temperature anomalies by country. So each country is each dot is on a country. We can see here as we move closer to nowadays is that it doesn't look good. That's now. And that was last year. So, if I had 6 months, I would just go and write something that would sort of make this a federated service on each server. Instead of having all these arrows, you would have one arrow per server. And I'm not joking, this is a lot of bandwidth. Even if your applications are doing nothing, they're still going to gossip. They're still going to exchange all this information. This is just a pure waste of energy, pure and plain and simple. Yep, so I think I'm through. And I think I ran pretty much out of time. There is a few articles here if you want to read to. These were the papers that were used to make this talk. And yeah, thank you very much.
So I'm a Kubernetes fanboy. So how does Kubernetes compare to these? Is it using these algorithms? Is it using something else? Have you worked with it?
Kubernetes is outsourcing all the clustering to etcd, and it uses one monolithic state that is sort of etcd replicates that in its key value store. etcd uses a quorum election, which is fairly, I think is quite Paxos-ish, and that's what Kubernetes uses. It doesn't really have a very elaborate failure detection, so it just pings the other servers. It's a deadline sort of thing. After 5 seconds by default, it goes, sort of says that the other part is gone. That's what Kubernetes is using, yeah. But you could also give the same information to Kubernetes that Akka is using. This is the same game, is who is there and who is not there.
Cool, thanks.